All right, so here we are, this machine learning security course, and we're up to chapter 6, decision trees. So let's start with the theory of decision trees and then go into the hands-on. All right, so we're going to talk about training and visualizing them, making the predictions, computational complexity, this concept of Gini impurity, how to regularize it, how to use a classification model and turn it into a regression model, and then a few more tricks. So decision trees are an amazingly simple machine learning model. And I don't know about you, my Twitch keeps getting blurry, and then it clears up after a few seconds. So according to my OBS, there's plenty of bandwidth, so I don't know what's causing that. But anyway, all right, so refreshing your browser often clears up a blurry Twitch. It's just strange how often it's happening to me here. All right, so a decision tree is just a series of if statements. Unlike the other neural models we've talked about, it's easy to understand how they work. You're not guessing, whereas the other neural models, models we make like neural nets, all the neurons are contributing to the answer, and it's not clear what any one neuron is doing, and it's not clear why it's doing what it's doing. So the decisions are interpretable, and you can combine them to make random forests, which are the most powerful type of model these days, apparently, or one of the most powerful. So training and visualizing a decision tree. Here's an example. If you take the iris data we talked about before, one of the classic machine learning data sets, which just measures 3 numbers having to do with the size of various features on iris flowers, and then you try to sort those flowers into categories, Setosa, versicolor, and virginica. So your original data set has 50 of each class, 150 samples, and then you do a single if statement. If the petal length is less than 2.45, you go this way, otherwise you go this way. If you go this way, now that's enough to completely split out this entire class of Setosa. All 50 of the Setosas are here and nothing else, so you're done. You've completely classified that one. Now all you have to do is classify the other 2. So here, you got 50 of one class and 50 of the other. So now you go to petal width. If it's less than 1.75, you go here. And if it's otherwise, you go here. And now, as you can see, you've got a very high degree of success here. Now you got 49 of one class and only 5 of the other. So you're about 90% correct. And over here, you got 45 of one class and 1 of the others. So you're like 95% correct, or 90, something like that. 98% correct. It's very good. So you're with just 2 if-then statements, you have pretty much sorted out the data here. And so one thing to watch here is this Gini number. The Gini is a measure of impurity made by combining the various probabilities. So if you have mixture of several classes, you get a high Gini going up towards 1. And if you're totally pure, you get a Gini of 0. So the goal of classification is to get the Gini number to be lower. So you have nice pure leaf nodes. These things are called nodes. This is the root node. And a node that has 2 arrows coming out of it is a split node that's getting split. And this is a leaf node, which is a node that does not go any further when you're at the end of the tree. And as you can see, your goal is to always lower the impurity. So 0.67 after the first decision goes down to 0 and 0.5. And after 0.5 goes down to 0.16 and 0.04. So each of these decisions is successful in lowering the impurity, which means you're more accurately classifying the data. Now you could, in principle, add another layer to this and try splitting these further to try to improve this, this classification, which is already pretty good. So if you want to make a prediction of this model, it's incredibly simple to traverse the tree. You just do one if statement, decide whether to go true or false here. So if you have this, petal length is 3 and petal width is 2, then the petal length is bigger than this and the petal width is bigger than that. So you have one comparison that's not less than, so you take the false. Another comparison that's not less than, so you take the false and you're done. So 2 if statements get you to the answer. So it is very fast to use a decision tree model. So the samples is the number of training instances this node applies to. The value is the count of instances in each class. And so that's what I said, this one had 150 samples, 50 from each of the classes. Gini impurity, here's the definition. You take 1 minus every probability of each class squared. So if here you have 1/3, 1/3, 1/3, So you take 1/3 squared times 3, which is a third, and you end up with 2/3. That's why this Gini impurity is 0.67. You have 3 classes all equally likely. And here's the decision tree boundaries. So the first boundary was here. The petal length is above or below this value. That completely perfectly cuts out these, and now puts these in the same category. You have to split them, and then they were split with a horizontal line, which, as you can see, is not perfect, but it's pretty good. There are some greens down here, and there's one blue a little bit too high, I think. So those are the errors we saw, and this is the split at depth 0. Here's the split at depth 1, and if you were to make the model beyond what our tree did and go to depth 2, you'd get these would each split like this to help split these further. All right, so like I say, it's interpretable, a white box. It's easy to understand how decisions are made, as opposed to neural networks that are black box. You have all these neurons throwing data around, coming up with an answer, but you can't really say what any one neuron is doing or why it chose one classification more than the other. So, if you want to estimate the accuracy, what is the probability that this thing is really Virginica? Well, the logical thing to do is here 45 out of the 46 training samples here were indeed Virginica, so that's the probability, 98%, 45 over 46. That's an way to estimate how likely your conclusions are. So they call this the CART training algorithm, classification and regression tree. You split the training set on a single feature with a threshold, like we did here, and then you find the values that produce the purest subsets, weighted by size. So you try to find the split that will most efficiently create 2 more pure nodes. So you can express that mathematically. You're going to split it into a left and a right subnode, and you can figure out the impurity, weight by the number of nodes, and the impurity here, weighted by the number of nodes. So you're just trying to, it's kind of obvious, you're just trying to get the most value out of this if statement that most efficiently separates the classes. That's it. And since you're only allowing one if statement on one parameter, you can't do more than split the classes into 2 groups, if there are more than 2 classes, like there were. So it's pretty simple. Now this is what's called a greedy algorithm. It only maximizes the value of the current split. It is not smart enough to think 2 or 3 moves ahead. It just gets the maximum value out of this one step and then tries it again. So that is a limitation of it. As you know, if you were to make a chess program this way, it would not be a very good chess player if it just tried to maximize the value out of every single move and it wasn't smart enough to make a strategy thinking several moves ahead. So that's the defect of greedy algorithms. They're fast to program and fast to implement, but they don't necessarily converge efficiently to the best solution, or necessarily at all to the best solution. All right. But the computational complexity is extremely low. If you have m training instances, then to go through the decision tree, you just need the log of m, log to the base 2 of m, because if you have the nodes here, the number of nodes here is approximately equal to training instances, and this is approximately the log of that. You only need to cut it in half. If you cut it in half every time, then you can decide among an awful lot of choices very fast. This is why you have the game 20 questions. If you ask 20 yes or no questions, you can pretty much answer any question you can think of, because that's really a lot. That lets you narrow things down to 1 in a million, because 1,000 binary choices is 1 in 1024. Or excuse me, 10 binary choices is 1 in 1024. So, that's the point. To use this is proportional to the log of the number of instances. In fact, to be more careful, it's the log of the number of classes. Well, log of training instances, I'm a little confused by that, but I thought it would be log of the number of features, but they say it doesn't matter. I guess that's true. You're assuming training instances are more than features. Anyway, and to train the model, it's n times m times log of m. So that's still pretty fast. Faster than a lot of other models where you'd have to go through the whole training set many times. Here you only have to go through the training set a log of m times. I'm confused by this place about a traversal being log m. Well, the point is here, if you consider how many of these nodes you're going to need, in the worst case, you might need 1 node per training instance. I guess that's what they're thinking. if it's very hard. So the number of total nodes is something like the total number of training instances. That's the part that makes me a little confused. I would think the number of total nodes, I guess that's right. So what I can certainly see is that you only need the log of the number of nodes. If there's this many nodes and you're just traversing down one branch, then you're only going to have to go through the log of them. Because if you have 1 here at this level, you have 2 at this level, 4 at this level, 16 at that level. But to resolve it, I only have to make one if statement per level. So this is clearly the log to the base 2 of the total number of nodes in the tree. M is the number of training instances, they say. And that's the part that seemed a little strange to me. I thought M would be the number of classes, would make a number of, yes, I know. If M was the number of classes, let me bring up the textbook and see if I've got this wrong. It seems to make more sense if M is the number of classes. So let me just check this, because I thought I understood it, but now I am not so convinced. Computational complexity. M independent of the number of features. M is the number of features is another number we haven't talked about here. We need to find out what M and N are. Okay. I wonder where they're going to tell me what M and N are. I thought I knew, but now I'm less confident. Okay, here's the sum to N. N is what? N is the number of classes here. This is the probability of classes. So it's like the N is the number of classes, and M has to be, I think, the number of training instances. Here's M. M is the number of instances. In the left, yep, okay. So M is the number of instances, and N is the number of classes. M is the number of instances, and N is the number of classes. So I shouldn't have this here. Number of features doesn't matter, but N is the number of classes. For instance, N, it's not listening to me. Still not listening correctly to me. Okay. No. All right, that's what it is. All right, now a number of features doesn't matter. Number of features is not even. The M is the number of training instances. That's what is a little confusing to me. I do not understand why the number of training instances matters so much. The number of nodes, I understand. It'll be the logarithm of the number of nodes. I don't understand why the number of nodes would be equal to the number of training instances or proportional to it, but apparently that's their assumption. If n equals 3, no, n does not, n equals 150. N is the number of training instances. The number of classes is, okay, let's get down here. N is the number of classes, right? N is 3 and M is 50, you're right. M is 150. 50 for each class, right? M is 150, exactly. You guys have got it right. And that's, so they're thinking there'd be 150 nodes in the tree because you have 150 training samples. That's the part I'm really not understanding. So I don't think I can clear it up. That is what it says in the book, but I think I'd have to read other reference materials to find out why they're saying that, because I certainly don't see 150 nodes in this tree. But I do see it's the logarithm of the number of nodes in the tree. Yes, this would take less than 7 decisions. I think that's a fair statement. Yes. So I think that's in the worst case, where it's most difficult, Then, still, if you split it in half each time, well, let's see if we can figure this out. If it was a most difficult case, then let me get a text page up here. You know, I'm beginning to have an understanding of this. If I can only, bad things are happening on my computer. I want a new page. All right, I've got a new page. All right, I got an idea. So suppose I had, let me make this font bigger. Whoa, there we are. So suppose I had like 64 here, and then I split them into 32 and 32, and then I split them into 16 and 16 and 16 and 16, and then I'm just trying to see if we can understand. Then I'm going to split them. I think this is the worst case, where each split does you the minimum value. Then, so the next row, I'm going to have 8 times 8 for each one. In the next row, I'm going to have 16 with 4 in each one. Next row, I'm going to have 32 with 2 in each one. And the last row, I'm going to have 64 with 1 in each one. So this, I think, is why, in the worst case, if you have 64 training samples, it will take you approximately 64 nodes to do it. You'll end up with a separate leaf node for each sample. So in this case, it would be the total number times about 2. So I guess this is the logic. The total number of nodes in the tree, in the worst case, would be approximately equal to the number of training instances. That's what I'm thinking. So in that sense, it perhaps does make sense, since remember, when you're doing this scaling stuff, you're not trying to be super accurate, and examples of small numbers are often off by quite a bit. You're trying to consider what will happen for large numbers and how fast it's going to grow with large numbers. So I guess this is why it's the number of samples that gives you a number that's going to tell you how big the whole tree is, and then it's the logarithm of the number of tree, of course, is log to the base 2 is how many levels it takes to reach a certain number. So I hope that helps. I think the book is correct. I think the book just assumes that we know a little more math than I do to understand that so quickly. All right, let's try a Kahoot. And I've got to find the right browser. All right. All right, there it is. Right, that's it. Worst case, you get every one thing in a class by itself after all the decisions. Exactly. There, all right. All right. All right. So what value are you trying to minimize? The Gini impurity. Minimizing that means accurately classifying into the classes. All right. All right, how much longer will it take to traverse a decision tree with twice as many nodes? One more step, right? Each step doubles the number of nodes. So that's the point of the logarithm. If you double the size of the tree, you only have to add one more step. That's what expanding with the logarithm is. All right. That's why it's very favorable. That means it scales very well. You can, if you make the number of nodes larger, the increased amount of time to use the decision tree does not go up hardly at all. All right, what advantages do decision trees have? All right, it has all these advantages. So more than one is the best answer. Faster to train, faster to traverse, and more interpretable. And ignore. Okay. Vooch. All right. So, let's go back to here. Good. All right, so Gini impurity we talked about is a measure if you have more than one class that is there. And the other way to do it is the old Shannon entropy, defined by Claude Shannon long ago. And that's the log of all the probabilities. A probability times the log of the probability, which is always negative, so minus sign in front. It's a number that gets bigger if you have a higher degree of disorder and gets smaller if you're all sorted into one class. So the same thing is fine. You could use either of these as a measure of the quality of the sorting, and you'll end up with about the same thing, as you can imagine. Doesn't really matter. Just like we talked about it before, you could use the sum of the absolute error or the sum of the squared errors or other related things like the logit, and in practice it doesn't really matter that much. You have some kind of measure of whether you're doing the job well or poorly, and you try to maximize the quality of your job. Now, you need some regularization hyperparameters, as we're going to see. This is a non-parametric model. The ones we talked about before are parametric. You'll choose something like a cubic with a certain number of parameters, and so you make an assumption about the data, like it's a line or it's a parabola or something, and then you have only so many parameters to fit. So it's only going to work if your assumption about the data is true and there's only so many parameters. But decision trees don't assume a shape. They're going to make as many decisions as they have to, as long as the impurity keeps going down. So there, in each decision is essentially a parameter. There's the parameter you choose and the threshold you choose. So that each decision node, they're adding essentially more parameters. So it will just add more parameters, adding more and more nodes. Doesn't have a fixed number of parameters. So therefore, it can have too many parameters and overfit the data. So you'd have to regularize it with hyperparameters. And there's a whole bunch of hyperparameters that all do pretty much the same thing. You can limit the depth of the tree, so it can only make so many decisions. You can limit the number of features evaluated for splitting at each node. That one just will speed it up. I don't think that will change the depth of the tree. That's the only one. The rest of these will all change the complexity of the tree. If you have a certain maximum number of leaf nodes, then it can't keep splitting it anymore after it reaches a certain number of leaf nodes. It can have a certain number of samples it must have before it can split, so it will refuse to split nodes that have not enough samples left in them. You can have the minimum number of samples a leaf node must have to be created, or a minimum fraction of the samples that must be in a leaf node. And as you can see, all these will pretty much do the same thing. They'll all stop it from growing without limit. And yeah, I do live next to an airport, so a lot of planes go over. All right. So There's another way to do this, where you first train the decision tree without restrictions, so it goes all the way to the limit, which is when it cannot split anything and improve the impurity. And then you prune it, deleting unnecessary nodes. And you can then decide if they are necessary. And the logical thing is if the purity improvement it provides is not statistically significant using a standard statistical test like chi-square. So that is a logical way to go. The non-statistically significant decisions you make are probably overtraining. So here's, with no restrictions, you can sort these things. This is the moon data we saw before that has curved data here and curved data here. With no restrictions, it will fit it very well with this bizarre model. With a region here, it's going to sort as orange, the rest is going to be yellow, and so on. And that's the kind of overfitting that will probably do well in the training data, but will not generalize to other data. And this is when you put in a regularization parameter, like you have to have at least 5 samples in all the leaf nodes. So now you get a much more reasonable model that approximately fits the curve here and the curve there. Notice it's all fit with straight lines because these are just if statements. So you're just fitting it with the lines always have to be horizontal and vertical too, because you only consider one feature at each time. So that's the limit of it. Now you can also use this model to fit to a curve. So instead of predicting a class, it's going to predict a value. You're trying to predict this value of some sort here. And so you've got true and false to predict a value. And if you look at it in a graph, here's what it is. You'll have something like a curve here, and it will fit it with just a bunch of horizontal lines. That's what it does. And this might seem like a terrible way to fit a curve, but this is in fact the way Riemann sums work and everything else. If you just have enough of these lines, you can get very close to the curve. So here's the cost function. You take the mean squared error, weight it by the left and right as we did before, and that's just mean squared error is just the distance for every sample between the value of the feature and the predicted value of the feature squared, just like we said, mean squared error instead of impurity. And so now, if you just let it go with no restrictions, it will overfit and spike up to hit every point. And if you put in a regularization parameter, like you got to have at least 10 samples in the leaf, then you get a reasonable, sort of jerky, but a reasonable following of the curve. Same thing as always, you need regularization to avoid overfitting. Another thing that is special to this model that you wouldn't see in any of the other models we talked about is it's sensitive to axis orientation. So here, if you have all the reds on the left and all the blues on the right, it can sort that. But if you just rotate it by 45 degrees, now it can't, because it can't draw a diagonal line. So if you rotate the data, now it's going to take more decisions to get there with this approximate horizontal thing. So the efficiency of the model depends on the parameters being independent. So there's this thing called a principal component analysis transformation that will rotate the data to try to reduce the correlation between the features. It will try to figure out where the logical place in however many dimensions you have to rotate it to, so that the horizontal and vertical lines will more likely succeed. So here's the result of PCA rotation. If you calculate these two things, Z1 and Z2, which are combining those features of like width and height of a petal, then you see in these parameters, it's really very good. Here's the original thing we had before, where all the yellows are over here, but now the blues and greens are also pretty much over here, so you can just use a horizontal line here and one horizontal line there and pretty much fit the data. Whereas it was much less effective before when we took the original parameters that were correlated, because of course the length and the width of a petal are correlated. A larger length probably has a larger width. So those are not two independent parameters. And that's why if you look at the original model back here, the original data here, see this is length and width. And of course, they pretty much follow a line here. The longer it is, the wider it is. So what you really want here is a diagonal line to separate those. So rotating this data will make this model work a lot better. It's a little obscure that PCA might be combining multiple features in each component. Yeah, well, that's what you call principal component analysis. So you would notice the trend here. You would say, well, what we really ought to do is make a variable here, which is like length divided by width or something. Because it looks like this is a constant slope. So every increase of 1 centimeter in the length means like half a centimeter in the width. So combining those two and having a parameter along here and then another parameter being distance away from this line, I think that's what they've done, then you'll see it's going along this line is all you need, and deviations perpendicular to this line don't matter at all. And that's what we got here. You have the one parameter Z1, which is the only one that matters, and Z2 doesn't seem to matter at all. So all you need is an if-then on Z1 and another if-then on Z1 to do the job. Yeah. Yeah, that's right. And this is a very good point. Digitizing a sound wave by sampling is the same thing. Let's talk about that. That's a good point. If you have like an MP3 that takes like 20,000 samples per second, this is what it does. You have a sound wave that's smoothly changing, and you take one sample, and then another sample, and another sample. That's what it is. And so the more samples you have, the more precisely you'll trace it out. But really, you never really are tracing it out. You're always just doing it with these spikes, with these horizontal bars. Although, of course, when you play it through an analog speaker, then it will naturally smooth it out. But anyway, that's the yes, that's the same thing as analog to digital conversion of a waveform. All right, and here's another thing that is kind of nuts. If you repeat the training, you will not get the same answer. Small changes may produce very different decision trees because it just is a greedy algorithm. It tries to dot a line somewhere, so even one small change might make it decide to make a different one, and it chooses the features to evaluate randomly, which feature to use. To use Audacity to see this? Well, I don't know if Audacity will show it to you. I just know in reality that's what analog to digital conversion always looks like. That is, you can have if you retrain the same model a few times, like you can just do it this way, or you can do it this way. So you could split it with a vertical line and then a horizontal line, or you could split it with two horizontal lines, and as you can see, it would be just as good. So these are two equally valuable ways to do it that are very much different. So that is a strange feature of decision trees, is you might get a completely different solution from a very small change. So that's why what we're going to talk about next week is the real cat's meow, which is a random forest. You don't use one decision tree, you make a bunch of decision trees, training them differently, and then you combine their output, like making them vote and take the majority, and that will of course smooth over this sort of strange situation where completely different decision trees might be equally good. Combining both of them would be better. Yeah. Yeah, and I'm not aware of any tool that ever showed me this thing directly. I just remember talking about it when I learned about analog digital computing, analog digital transformation, which of course you use in all kinds of instruments. I wasn't aware of anything that actually displayed this, but this is what's really going on. The only thing I know that displays it is the Riemann sum. If you learn integrals in calculus, they do it as a sum this way, where you take intervals and you calculate this rectangle and add this rectangle and add that rectangle, and then you take the limit as the width of the rectangles goes to 0, and then you arbitrarily closely fit the curve. Yeah. All right, let's try another Kahoot. I see a lot of intelligent comments in the chat. This is great. By the way, in a real sound card, it wouldn't look like that because a real sound card has got electrical overhang and stuff. So what you'd actually get would be kind of horrible. If you'd get some overhang here and some oscillation and some errors. So it wouldn't perfectly fit this. This is a mathematical expression. The decision tree really works this way. Any real mechanical or electrical device is going to, in fact, smooth this out and distort it in other ways. Anyway, all right. is great. I appreciate the intelligent comments. That'll help me improve this course. All right. All right, so which models make assumptions about the data? Those are the parametrics. So if you choose, for example, a line that only has 2 parameters, it will do a lousy job if the data doesn't really follow the line. All right. All right, what process smooths the model so it will generalize better? That's regularization, where you limit the amount of variation the model is allowed to have. We've done it in the past for all these models, like removing the high-order polynomial terms and so on, just not letting it follow the data as precisely, forcing it to go through it with a smoother curve, which we hope will follow the actual trend of the underlying phenomenon and not the noise in our particular set of samples. All right, which process rotates the data? That's it, principal component analysis. All right. All right, that's Ant ignores 1 twice. And Greg wins. And Woot has won twice. All right, I'm going to stop this recording. I can find my OBS.